Hey, what are you doing? If you want to know what he was removing from transformer architecture to convert it into ChatGPT, watch the video.
Like and subscribe.
Welcome back to episode 9 of our Transformer series. In the last episode, we looked inside the encoder and understood how a transformer read and understand a sentence. Today, we go to the other side. We look inside the decoder. The decoder is a part of the transformer that actually writes. It generates text one word at a time. And the way it does, that is beautifully designed. Let us break it open and see what happens. We established in previous episode that transformer has two halves. Now let's give them clear roles. Think of it in this way. The encoder is a reader. You hand it a full sentence and it reads every word, building a deep understanding of the meaning. The decoder is a writer. It takes the understanding and produces new text. The encoder receives the complete input. It processes all words simultaneously. Its job is to understand. At the end of its work, every word has a rich representation that captures not just its own meaning, but its meaning in context. That understanding flows from encoder to decoder. This connection is critical, and we will see exactly how it works when we get to cross attention. The decoder's job is different. It does not see the entire output at once. It produces one token at a time. Each new word depends on the word it has already generated. This is the key distinction. The encoder reads in parallel. The decoder writes sequentially. Let us see that sequential writing process in action with concrete example. Imagine we are translating from English to French. The encoder reads full English sentence. The cat sat on the mat. All 6 words processed together. Now, the decoder must produce the French translation. Here is a critical part. The decoder does not produce the entire French sentence at once. It generates one word, then use that word to help generate the next one, and so on. This process is called autoregressive generation. Each new token depends on all the previous token. The decoder starts. Its first output is Li. That is it. One token. Now it takes that token and feeds it back in. With Li as a context, it generates chat. Now it has Li chat as a context for the next step. Li chat is each step the decoder looks at everything it has generated so far and makes a decision about the next word. Now French is not my forte, so pardon my French. Li chat is assis, the cat is sitting, right? Translation complete. Notice the pattern? At step 1, the decoder had no prior context. At step 4, it had 3 previous words, guiding its choice. This is why order matters. This is why we need the masking we will see next. Now that we understand what the decoder does, let us look at how it is built. A single decoder layer is a stack of 3 sublayers, each with its specific job. At the top, you see the first sublayer, masked self-attention. This is where the decoder looks at the token it has already generated. The second sublayer is the cross-attention, also called as encoder-decoder attention. This is the layer that encoder does not have. This is what makes decoder special. It is the bridge between reading and writing. Through cross-attention, the decoder can look at the encoder's output and ask which part of the input are most relevant right now. The third sublayer is feed-forward network. Same architecture as in the encoder. It processes each token independently, adding non-linear computation after the attention layer have mixed the information. So, compared to encoder, the decoder has one extra attention layer. The encoder had 2 sublayers, self-attention and feed-forward. The encoder has 3, masked self-attention, cross-attention and feed-forward. Each sublayer is wrapped in a residual connection and a layer normalization. 3 sublayer, 3 residual connection. That is the anatomy of one decoder layer. Let us now zoom into each one. The first sublayer in decoder is masked self-attention. We already know how self-attention works from the encoder. The decoder version is almost identical, but it has one additional constraint. Think back to that exam analogy. You're writing an exam. You can look back at your previous answers, but you absolutely cannot flip ahead to see answers you have not written yet. That would be cheating, right? This is the fundamental rule. When a token computes its attention score, it can only attend to the token at earlier position. It cannot look ahead. And this makes perfect sense for generation. When a decoder is producing the third word, only the first and second word exist. The fourth word has not been generated yet. Looking at it during training would be giving the model the answer. Let us make this concrete. While the model is predicting what comes after love, it can see I and love. Those are the past. It sees itself in the current position, machine, but it cannot see learning. That token is in the future. The model must predict it, not copy it. This rule is not enforced by magic. It is enforced mathematically using something called as causal mask. It is simple but powerful mechanism. Let me show you exactly how it works. To understand the causal mask, let us look at the attention matrix directly. On the left, you see what the attention matrix would look like without masking. Every cell is green. Every cell contains a 1. This means every token can attain to every other token. This is what the encoder uses, full visibility. Now watch what happens when we apply the causal mask. Look at this. The lower triangle remains green. Those are the allowed connection. Token 1 can see only itself. Token 2 can see token 1 and itself. Token 3 can see first 3 tokens. Token 4, being the last, can see everything, but the upper triangle is completely red. Those are the block connection. The zeros. No token is allowed to peek ahead. This is the causal mask. Simple and elegant. During training, the model processes the entire sequence at once for efficiency. But this mask ensures that each position's prediction depends only on earlier position. It is as if every token is wearing blinder that only allow it to look backward. The first sublayer handles the decoder relationship with its own output. Now we move to the second sublayer, and this is where things get really interesting. This is cross attention. The decoder has generated some words, but those words alone are not enough. The decoder also needs to understand the input. It needs to know what the original sentence say. Cross attention is the mechanism that lets decoder consult the encoder. Think of it in this way. The decoder is a writer working on a translation. Self-attention lets the writer reread their own draft. Cross-attention lets the writer look back at the original document they are translating from. Look carefully at this diagram. The query, the Q, comes from the decoder. That is, the decoder asking the question, what part of the input should I focus on? The key and value, that is K and V, comes from the encoder. That is, the encoder stored understanding of the input. This is the key asymmetry. In self-attention, Q, K and V all come from the same sequence. In cross-attention, Q comes from one sequence and K and V comes from a different sequence. Let me say that one more time because this is the single most important mechanical fact about cross-attention. The decoder creates the queries. The encoder provides key and values. Attention scores are computed between decoder queries and the encoder keys. Those scores determines how much each encoder value to retrieve. This is why it is called cross-attention. It crosses the boundaries between two sequences. The decoder sequence and the encoder sequence interact through this mechanism. Let us see cross-attention in real example to make this concrete. We have our English input, the cat sat. The encoder has processed these three words and produced a rich representation from each one of them. Now, the decoder is generating the French translation. It has produced Lee, chat, and is now working on assist. Watch the arcs. When the decoder generates assist, which means sitting in French, it attains most strongly to sat in the input. that thick cyan arc represents high attention weight, and the model has learned that sat in English directly correspond to assist. In French, there is a weaker connection to cat because the subject matter stew, right? And the gets very little attention because it has no relevance for this particular word. This is the power of cross attention. The decoder has not blindly used the entire encoder output. It selectively focuses on the part that matters most for each word it generates. For each output token, the attention distribution over the input token is different. When generating chat, the strongest attention was probably on cat. When generating assist, it's shifted to sat. Now, step back and see the bigger picture. The decoder has something that encoder does not. It has two distinct channels of information flowing into it. Source 1, the token it has already generated, this information comes through masked self-attention. The decoder rereads its own draft to maintain coherence and grammatical structure. And it's combined that with source 2, the encoder's understanding of the input. This arrives through cross-attention. The decoder constructs the original material to make sure it captures the right meaning. These two streams merge and the result is a next token prediction. Past context plus input meaning together produce the next word. Neither source alone would be sufficient. Without self-attention, the decoder loses track of what it has already said. Without cross-attention, it forgets what input actually means. This dual source architecture is one of the fundamental reasons that transformer works so well for tasks like translation, summarization, and any task where you need to read one thing and produce another. We have covered the first two sublayers, mass self-attention for internal coherence and cross-attention for input understanding. The third sublayer is feed-forward network, and it serves a different purpose. After the attention layer have mixed information across tokens, the feed-forward network processes each token individually. Think of attention as group discussion, where tokens share information, and feed-forward network as individual thinking time, where each token processes what it learned. The formula has two steps. First, multiply the input by weight matrix, add a bias, and apply a activation function. The activation function in this case is very simple. If the value is negative, set it to 0. If positive, keep it as is. Second, multiply by another weight matrix and add another bias. The first step expands the dimension in the original transformer from 512 to 2048. The second step compresses it back to 512. But why expand and then compress? The expansion creates a larger space where the model can perform more complex computation. The compression brings it back to the model's working dimension. This bottleneck design is efficient and powerful. Look at this graph. On the left side, everything negative is clamped to 0. On the right side, the value passed through unchanged. This is the activation function. Simple, but it's introduced the non-linearity that allows the network to learn complex pattern. Without this non-linearity, stacking multiple layers of attention would just be equivalent to one big linear operation. We now know the three sublayers, but there is one more structural element that appears at every sublayer, and without it, transformer simply would not work. Look at this diagram carefully. The input goes into sublayer that could be masked self-attention, cross-attention, or feed-forward network. But notice the dashed gold line at the top. That is the skip connection, also called as residual connection. A copy of the original input bypasses the sublayer entirely and meet the sublayer's output at the additional point. This means the output of each sublayer is the original input, plus whatever the sublayer learned. If the sublayer learned nothing useful for a particular token, the information still passes through unchanged. After the addition, layer normalization stabilizes the value. Without normalization, as you stack 6 or more layers, the number can grow very large or very small. Layer normalization keeps the value in well-behaved range. These two techniques together, residual connection and layer normalization, are what allow the transformer to be deep. You can stack many layers and still train the model reliably. The gradient flow cleanly through the skip connection during backpropagation, and the normalization prevents numerical instability. Now let's put everything together and trace the complete data flow through one decoder layer. Token enter at the top. These are the embeddings of the output token generated so far, combined with the positional encoding. The first stop, masked self-attention. Each output token attains to all previous output tokens, but not the future ones. The casual mask enforces this. The result passes through add and norm, residual connection plus layer normalization. Second stop, cross connection. Now, the decoder reaches out to encoder. The decoder current state generates the query. The encoder's output provides the key and value. The attention scores tell each decoder token how much to focus on each encoder token. Another add and norm follows. The third stop comes. This is the feed-forward network. Each token is processed independently and an activation function is applied. The dimension is expanded and then compressed, and then one more add and norm layer is added. And the output representation emerges at the bottom. This representation carries information from three sources: the token's own history, the encoder's understanding of the input, and a non-linear feature processing. The original transformer paper used 6 of these layers stacked on top of each other. The output of one layer becomes the input of the next one. Each layer refines the representation further. By the time the data exits the 6th layer, the model has highly processed representation ready for the final prediction. Before we close, there is a fascinating historical development that connects everything we have learned today to models you use every day. On the left, you see the original transformer from 2017 paper. It has both an encoder and a decoder connected by cross attention. This design was built for translation. Read one language, write another. But a researcher at OpenAI asked a different question. What if you do not need to translate between two sequences? What if you just want to generate text from a single stream of words? This is the GPT architecture. It keeps only the decoder. Cross attention is removed because there is no encoder to cross attend to. The encoder itself is removed entirely. What remains is the masked self-attention layer and feed-forward network. That is it. The model we talked about today minus one sublayer. This design works because for language modeling, you do not have a separate input sequence. The input and the output are the same sequence. You predict the next word based on all previous words. And that is exactly what masked self-attention does. So, GPT took decoder's core mechanism, autoregressive generation, with casual masking, and built an entire language model around it. Every GPT model, every ChatGPT interaction runs on the decoder-only transformer. The architecture you study today is the architecture behind most widely used language model in the world. Now you see 4 questions on your screen. If you could answer them, then you have understood the material. If you cannot, please go back and review. So, pause and ponder. If you found this video helpful, leave a like and subscribe. In the next video, we go deep into masking. We will look into casual mask, padding mask, and how masking is actually applied inside the attention score matrices in real implementation. That is where the maths meet the actual code. And it is the detail that almost every tutorial skips. I'll see you in the next one.